This print failed at hour 6. The fracture line traces straight back to the first layer a corner that lifted 0.05 millimeters on layer 1. By layer 50, that gap became a crack. By layer 300, it became a clean break. The first layer isn't a setting. It's a contract between machine, material, and physics. Break any term and the part fails later, often catastrophically. This video shows exactly where those terms lie, in microns and newtons. Bed leveling starts with a feeler gauge, not paper. Standard printer paper runs 0.07 to 0.1 millimeters thick, a range wider than your acceptable nozzle gap. A proper 0.1 millimeter brass shim eliminates the variable. If your nozzle drags the shim with slight resistance at 4 corners and center, your tram is within 0.02 millimeters. That's the window. Wider and the first layer doesn't squish. Tighter and you gouge the PEI. Z offset is where the contract gets signed. 0.01 millimeter steps. Live adjust while printing a single wall calibration square. Watch the extrusion width go from 0.38 too high to 0.48, squished to 0.42, target for 0.4 nozzle. That's a 3-click window on most printers. Save the mesh. Then verify cold thermal expansion of the aluminum bed shifts 0 by up to 0.03 millimeters at 60 degrees. Surface energy decides adhesion force. Clean PEI gives water contact angle of 30 degrees 72 millinewtons per meter. Wipe with isopropyl, it drops to 22 degrees 80 millinewtons. Glue stick pushes it to 10 degrees 90 plus, but hairspray? Inconsistent. Magigu Original hits 15 degrees reliably. The difference between 30 and 15 degrees is 2 times the work of adhesion. That's the margin between a part that stays and a part that walks. First layer height 0.2 millimeter. Nozzle 0.4. Line width 120% equals 0.48 millimeter extrusion width. The math: you're pushing 0.06 cubic millimeters per millimeter of travel through a gap 40% smaller than the bead. That pressure, roughly 8 bar, forces polymer into the PEI texture. Drop to 0.15 millimeter height and pressure spikes to 15 bar, causing elephant's foot. Raise to 0.25 and pressure has no mechanical interlock. Low-rate calibration uses a single wall cube measured with digital calipers at 4 heights. Target wall thickness 0.4 millimeter, 1 nozzle diameter. 95% flow gives 0.38 gaps between lines. 100% gives 0.40. 105% gives 0.43 lines fuse, but elephant's foot grows. The sweet spot is 98% for most PLA. That 2% window is narrower than your extruder's stepper resolution on a standard Bowden setup. Bed temperature gradient kills flat parts. 22 centimeter bed, 60 degrees center, 52 degrees corners, 8 degree delta, measured with 4 thermocouples taped to the glass. PLA coefficient of thermal expansion, 0.07 millimeters per meter per Kelvin. 8 degrees across 220 millimeters equals 0.12 millimeter differential contraction. That's enough to lift a corner off the bed at layer 3. The fix isn't hotter bed, it's insulated corners or a thicker plate. A draft you can't feel moves 15 degrees of heat in 3 seconds. Smoke pencil at 10 centimeters from bed shows 0.5 meters per second crossflow from a ceiling vent 3 meters away. First layer cools from 60 to 45 before layer 2 arrives. That thermal shock locks in warping stress. Enclosure isn't luxury, it's process control. Cardboard box around the printer cuts draft velocity to 0.05 meters per second. First layer stays at 58 degrees. Part survives. Brass nozzle wears. 500 grams of carbon fiber nylon increases orifice from 0.40 to 0.42 millimeters. First layer geometry changes silently. Line width grows 3%, layer height effectively drops 5%, squish pressure jumps 20%. You compensate with flow and Z offset, but the worn edges deposit ragged beads that don't fuse. Swap the nozzle. 10 cents. Measure the new one with pin gauges, don't trust the stamp. 0.4% water content. In PLA, that's 4 hours in a 20% humidity shop, creates steam bubbles at 210 degrees. First layer sounds like bacon frying. Microscopic voids form at the bed interface, reducing contact area by up to 30%. Dry box at -20 dew point for 6 hours restores adhesion to baseline. The pop test: extrude 10 millimeters into air. Silent stream means dry. Snaps and sputters means dry at first. First layer speed changes polymer viscosity. 20 millimeters per second. Shear rate low, viscosity high, bead lays down thick. 30 millimeters per second. Shear thinning drops viscosity 40%, bead spreads wider, squish pressure drops. 10 millimeters per second. Residence time doubles, heat soak expands filament in the melt zone, over extrusion. The viscosity curve for PLA at 210 degrees crosses the critical shear rate at 22 millimeters per second. That's your speed limit. Brim adds 5 millimeters perimeter contact. On a 20 millimeter cube, that's 40% more adhesion area for 2 minutes of print time. But removal peels the first layer off the bed, damaging the PEI. Raft wastes 30 minutes and leaves a rough bottom. Skirt only primes the nozzle. The engineering choice: Brim for tall, thin parts, nothing for wide, flat parts, and always chamfer the first layer corners. In the slicer, 0.4 millimeter 45 degree chamfer reduces peel stress concentration by 60%. The hidden failure: residual stress locked in the first layer. X-ray diffraction on a warped 20 millimeter cube shows 15 megapascals tensile stress in the bottom 2 layers, stress that doesn't relax because the bed constrains it. By layer 50, the part is still flat. By layer 200, the accumulated contraction overcomes bed adhesion. The fracture initiates at the first layer corner. You can't see it. You can't measure it without XRD, but you prevent it by keeping first layer temperature uniform and cooling slow. The first layer is a contract. Nozzle gap 0.10 plus minus 0.02. Bed temp 60 plus minus 2 degrees. Flow 98%. Speed 22 millimeters per second. Dry filament. Clean PEI. Chamfered corners. No drafts. Fresh nozzle. Every term measurable. Every term enforceable. Break 1 and the part fails at hour 6 or day 30 under load. The calibration files that verify every term are free at Gildson Grains. Com.